Okay, it should be recording now. Hello. Welcome to the 7th recitation. And today again we have code review, so that should be fun. And you guys will get a chance to talk to each other and show each other your code and hopefully. And we got good feedback last time, so I think you guys will enjoy it. Yeah, I guess there's just a lot more work piles up with exams and stuff before the break, so it's just natural to feel more tired. Yeah, so the procedure for, okay, I guess I'll just get started here. Okay, so yeah, today we have code review and then we'll have a little discussion and then we'll just talk about assembly. And yeah, so PA2 grades are out now and Prince and Azita are the graders this time around. So if you guys have any questions, just feel free to email them. And so here's the attendance form and it's the same attendance form as last time, but this time the points will get added to your PA2 scores. And I'll paste this link in the chat. And yeah, so you guys can go and take attendance there. Is the link working for everyone? Are you able to access it? All right, cool. Nice. Yeah, so we'll get started with code review in another minute. So basically, I'll be putting you guys into breakout rooms. And this time, last time we had 5 people per room, but based on the suggestions in the survey, the anonymous survey that we had, it made more sense to do 10 people. And yeah, so and people also people find it more helpful to share programs that they lost points on. So that's something I wanted to highlight. So you guys should definitely do that. And yeah, talk about your different implementations, offer feedback. And a new thing that I wanted you guys to take a look at is differences in code length. So programs with a lot more code may produce the same output as a shorter length program. So I want you to look out for that, and then we'll talk about that more later. Yeah, so I guess I'll just split you guys up now, and then we can get started with code review. Okay, yeah, so I created the rooms and they're open, and you guys could go join the breakout rooms now. Oh, really? I mean, that's good because you guys, yeah, I guess you guys got more experience of what it's going to be like last time, so we were able to improve it. Did you like it better with the 10 people, around 10 people per breakout room?
Yeah, I liked it more. There were actually like more people like talking and stuff like that.
Yeah.
Went better.
Yeah, I just thought that it might be hard for everyone to share their code, but it makes but yeah, I guess if you guys like that better, we'll keep it that way.
We're supposed to show our code in the code review, right?
Oh, yeah. Yeah.
I know, because we're always told so much not to show our code to our peers. So, everyone is leery.
Mhm. Yeah, but it's fine during code review because the programming assignment's already done and submitted, and we want you guys to get feedback from your classmates. Yeah, so did you guys notice like cleaner code this time based on what we talked about last time? Yeah, well, I did pop into some breakout rooms, and the code that I saw had good code quality, so I think it did help. And yeah, it would be pretty hard to give everyone individual feedback, but I think this is a pretty good balance. And yeah, so did you guys take note of the differences in code length and how some people might have way longer programs than others for the same, to achieve the same goal?
I think
Yeah.
I
Oh.
think time is a limiting factor. I know I made some of the mistakes, maybe other people didn't, and I left some of my variables in, even though they were not completely used. But yeah, I mean, if I had more time, I would have cleaned it up nicely. But
That's fair. Yeah. hmm
sorry, whoever was speaking, I interrupted. Sorry.
That's okay. You basically said the same thing I wanted to say. It's all right.
hmm Um, yeah, so I guess that was good, and we'll keep doing code review. Well, the next assignment is gonna be okay. We'll probably have code review for that too, and then um, there will be an assembly assignment. Okay, so this is something that the professor wanted me to emphasize, and she wanted all the TAs to emphasize this. And so it's this concept of less is more. And so the professor's been noticing that some students have been writing way more code than required to solve the problems. And so this third programming assignment, it's here to test your knowledge of bitwise operations, not specifically, and well, so you're not supposed to really write a lot of functions to convert between bases and stuff like that. All that's supposed to be happening through bit shifting and masking. And yeah, so a lot of things can be accomplished by shifting and masking. And many times you won't have to write a separate function to do stuff. And you could use bitwise operations to do that. And yeah, so just like try out different operations and see what they do and see how that could help you. So yeah, these pieces of code should not be too long. And yeah, so just keep this in mind when you work on it. And now let's talk about assembly a little bit. We only have 15 minutes, so I'm not sure if I'll be able to get through everything that I had planned, but I hope that we could get through most of it. Okay, so the first thing that I want to talk about is what kind of operations are available in assembly. And so we can basically perform arithmetic operations on register or memory data. So, and then, so we have memory and we have registers on the CPU, and you could transfer data between the two. And you also have control flow. And so you have if statements, while loops, you have for loops, and you have, you could kind of think of them as go-to statements if you're familiar with that. You basically just tell the program to go to a specific piece of the code when that line is executed. And so yeah, you could split up your assembly programs and tell the computer that you want to go to a specific piece of code. And then okay, so basically the CPU has registers, right? Because the CPU needs to keep track of some data so it could perform the calculations on it. And so registers are basically temporary storage areas that are built into a CPU. And it's not much storage, it's a small amount, but it's very fast. The CPU is able to access this data very quickly and perform operations on it. And yeah, so registers basically serve as this kind of bridge between your main memory and your processor. So if you want to send data over to the processor from memory to do some calculations on it, you need to use registers. And so these are the registers that we'll be talking about in the version of assembly that we're working with, which is x86-64. And so these are 64-bit registers, 8 bytes. And so everything here other than RSP and this is supposed to be actually RBP, not BSP. So I'll correct that when I post the slides. But yeah, everything other than these two are general purpose registers. And so you see that we have these registers here, RAX, RBX, RCX, and then we have these gray portions. And the gray portions are basically half of the register, which are 4 bytes in 4 bytes long instead of the where did we talk? Oh, right here. Instead of the 8 bytes of the entire register. And so these names that we have of the registers here, EAX, EBX, ECX, these were the names that were used in 32-bit CPUs and are used in some 32-bit CPUs today. And yeah, so we are still able to access these pieces of the register. And so there is backwards compatibility in this way because we're able to access. So now we're kind of zooming in. So if you go back, we see that we have the complete RAX and then we have EAX. So let's zoom into just the gray portions. And so you have these registers here, and these registers have their own portions, right? Their own pieces of the register that you can access. So this is now, if you want to get, so we had an 8-byte register, and then this is a 4-byte register. And if you want to split that up more, the AX is a 2-byte register. And then you could even access individual bytes with these names that are given to it. And so there is backwards compatibility here. So when computers shifted from 32-bit to 64-bit, they preserved this backward compatibility. So you're able to still access those sub pieces of the register. And I mean, yeah, so this is the origin of the names of the registers, but you guys will learn more about this later and why this is the stack pointer and the base pointer and how that works. But for now, let's just move on to talking more about assembly. And so we can move data from, so yeah, moving data is a pretty critical part. So moving data between the memory and the registers, that's a critical part of what assembly is used for. And so we have 2 parameters here for the move Q instruction. The Q here kind of just, it kind of signifies how big the piece of data that you're moving is. But we don't need to go into in depth with how this was named. So we have a source and a destination. And so let's say we wanted to move a number into some register. So we would write the move Q, and then the first parameter we'll pass is 123. Let's say we wanted to move the number 123. And then before the 123, we have to place a $sign because we're passing a constant. And if you're passing a constant, the $sign is necessary. And then the percent here signifies that you're talking about a register, and then you put the name of the register, RAX. So this moves this value into this register. And yeah, so we can also move things between registers. So we could do, okay, so we have a bunch of different ways to move things here. So this is moving immediate values, such as this value here. This isn't hexadecimal, but it could be written in any base. And And then we have the negative 147. And yeah, so basically, you see here that that here the percent RAX is not surrounded by parentheses, but here it is surrounded by parentheses. And what the parentheses mean is actually dereferencing the register. So let's say, okay, so let's go through the first line first. So this is moving this value into the register RAX. So this is equivalent to in C saying temp equals 0x4. And for this piece of code, this is equivalent to doing star p equals negative 147 because the parentheses around the RAX actually dereference dereference what's in the register. So let's say if you have a memory address that's stored in the register, you dereference the register, you get the memory address, and then you store negative 147 into that memory address. So if we just did negative 147 and percent RAX without the parentheses, that's like saying you want to move the value negative 147 into the register. But let's say the register already contained a piece of contained a memory address that you wanted to move it to. Then you would do the parentheses because then it would dereference what's in RAX and move your negative 147 into that, which is the memory address that you'd want to move it to. And then there's a few more examples here. This is moving between registers and memory again. And so we could move like a value from one register to another. So by doing RAX and RDX, it moves the value in RAX to RDX. And the move is actually kind of it's kind of inaccurate because it's not really moving the value. So it's really copying the value because the value still stays in RAX. It doesn't just go from RAX to RDX and then RAX is empty. It stays in both, but it's the instruction is still called move. And then this is what we talked about before. We could take the value in a register and move it to a memory address, which is what we're doing here with the parentheses, which dereference it. And then we have another example here where we're moving something. We're moving the memory address or any value that's stored in RAX into the register RDX. And yeah, so that's basically how that would work. And
I have a question.
yeah,
So is anything with a pointer, is that just like data that's in the memory? And then anything that's not in a pointer, that's stuff that's in the register?
yeah, basically.
Okay.
Yeah, so that's how you could kind of see compare it to C. And then we have simple memory addresses where if you have a memory address R in then that means it's in memory. It's in the memory at the value at register R. And this will make more sense once we get to the next slides where we go into more complex memory addressing. And we could see how this is like pointer dereferencing in C. So if you dereference RCX using parentheses, you can move the value into RAX. And then we also have this thing called displacement here. So you could basically start at some register, and you could add a value to it. So let's say you had RBP, but what you really want to do is go to so let's say you have an address in the register RBP, but you really want to do is get something from 8 bytes over from address RBP. So if you put an 8 next to the parentheses, that means we take RBP, add 8 to that memory address, and then dereference it. So this 8 on the side here just means it signifies addition. So so if we have any value D next to the register in parentheses, that means we're accessing the memory at the register at whatever is at the register R plus D. Just add 8 without dereferencing it. What do you mean? So we want to access the value at memory at this location. So we want to add 8 and then so we have a memory address in RBP. We want to add 8 to it and then dereference it to see what's actually in that memory address. Add 8 without dereferencing it. You wouldn't really need to do that, but we have more. I have another slide with all of the arithmetic operations you could do. So you could perform addition and subtraction and all of that stuff in assembly. No, it's not always a multiple of 8. That was just an example. It could be any displacement value that you want. And this isn't like C adding. So when we add like 8 in C, it'll see the type of value that's there and add the size of that times 8. But this just straight up adds 8 bytes to it. And then I think, yeah, so we only have like a minute left. So this is the only thing I'll be able to get through. But I'll definitely cover this in the next recitation more. And then I'll also post these slides so you guys could take a look. And at 6:10 you could leave if you don't have time. But I guess I'll just go over this quick assembly code and then I'll end this and post the recording. So basically here we have this function in C. It's called swap. And it has 2 long pointer values, right? So what we want to do is, so we store in T0 the value in XP by dereferencing it, and then we store in T1 the value in YP by dereferencing it. Then we take star XP, which is the value at the pointer XP, and we assign T1 to that, and then we take the value at YP and assign T0 to that. So that effectively swaps the 2 values. And we could do the exact same thing in assembly, but using these instructions. So first what we want to do is, okay, so I guess if I go to this slide, it'll be clearer. So first what I want to do is I want to move, okay, so let's define which register values contain what. So let's say RDI contains our XP, RSI contains YP, RAX contains T0, and RDX contains T1, right? So if we're moving, so first what we want to do is we want to take the value in RDI. So we want to take RDI, dereference it, which is exactly what we're doing here. We're dereferencing XP, and we're moving that into RAX. And so we're moving the value in XP into T0, which is RAX. And no, percent RDI and percent RSI are the actual register names. And yeah, so when you write out their names, you get the value in it. Yeah, so you get the pointer. And then if there's a memory address, yeah, so we dereference it and we send it over to RAX. And then we dereference RSI, which contains YP, and we move it over to RDX, which is exactly what we did here. We moved the value in YP over to T1, and T1 in our case is RDX here. And then we just move the value that's in RDX now, which is the value in T1, over to the memory address in RDI. So we move the value in T1 to XP, and then we move the value in T0 to YP, which is RSI, and then we return. And so that effectively does all of these operations for us, and we're able to swap 2 values like that. And Yeah, so I had more planned, but we'll get to the rest of the stuff later. And these are just all the arithmetic operations you could do in C, or some of them, in assembly. And then we have, I just have a list of operations and another example. But we'll go over these next time, and I'll also post this recording and presentation. And so you guys could take a look and try to make sense of it yourself. Yeah, no problem. Yeah, I'll stop the recording now and I'll end the recitation. So